I don't think we've tried this before, right? I guess, long time ago.
First time.
Yeah.
At least as far as I know.
Yeah. I think Alex did once with Justin Drake, like smaller, with a smaller group. But yeah, this is, let's just say, first time we're doing a live whiteboard. So, that said, we always do them without preparation anyway, and in one take. So this is not that different.
Yeah.
But if you have questions, raise a hand and we can dive in. So today we wanted to just go over kind of the tech stack we're building because it's kind of getting more and more complex as there's more and more moving pieces, which are also built by different teams, and like all of those different teams contributing effectively into like one master stack that we're trying to enable with this vision. But yeah, it would be good to actually have like all of this outlined, and yeah, if there's any additional questions, we can cover them. So I'll just draw the stack, and then we can kind of go line by line. So actually, something that long time ago, when we started near blockchain, we were trying to figure out how to do networking stack, and we've implemented a version of it. But one of the challenges generally with blockchain has been there's no incentives on a networking level, right? You're kind of hoping somebody will give you data, and there's no kind of way to identify if somebody did not give you data.
Or to punish.
Or to punish, yeah, if they didn't give you data. And so one of the protocols we actually released last week, it's called proof of response. And so it's a new primitive that really enables a way to prove when somebody is not responding to you, to everybody else. So then, obviously we have the blockchain itself. We have the chain signatures. I would actually put the TEs here before intents.
Yeah, sure. This is the TE cloud?
Yeah, TE cloud.
Yeah.
We have intents. And then we have AITP. And I mean, there's more things, but let's just kind of focus on these. So all of them kind of using stuff underneath or planning to use or kind of depend on what's built. But also there's kind of maybe indirect dependencies. So maybe let's start with proof of response, right? So one of the, again, as I stated, the problem been, okay, I am Alice, right? And I want to get some data, a very simple, question from another node, and that node doesn't respond to me, which can be it's offline or it just decided that it doesn't want to respond to me. And traditionally, there's literally no way to prove to anybody else that this is happening. And so the question was, like, why this is important? Let's start with this. Well, if this node stores your data, right? So let's imagine this is a data storage protocol like on Machina, right? And that node like stores your data. There's a proof on chain that it stored your data. But then when you actually go and reach out to it, it doesn't give you the response. It doesn't give you the data. Like there's no way to tell to the network that like, hey, this node is not doing this. Now, for our agentic internet, it's even more important because this node can be running some agent, right? And this agent maybe even have some private data or access to some APIs. And so again, if you depend on this agent for your for your interactions, like this is agent that rebalances your portfolio and it doesn't reply, you need at least find some alternative. And ideally also find a crypto-economic way to punish it. So what kind of proof of response introduces is a network of relayer nodes which are interconnected, and so with service nodes as well. And on each edge in this network, there is some effectively latency and cost. And so when I'm joining the network, right, as Alice, I now specify a path. So let's say I'm trying to retrieve some data that I want my request to take. And I'm paying a little bit. So there's a payment channel established. I'm paying a little bit for this request. So what are different cases, right? One case, this replies back, and the information goes back to Alice. She's happy. She paid a little bit for the networking. Now we have a networking protocol for incentivizing actually information exchange. Now it's possible that this node, let's say Bob, doesn't want to reply to Alice, and for example, it didn't actually store the data. And in this case, again, two options. One is it replies with just an empty response, right? Like, hey, there is a reply. And so Alice, but because it's a cryptographically signed reply, Alice can then show to the network, hey, Bob replied me with nothing for this request. This is a malicious behavior. The other option is he just ignores, right, and doesn't reply. And so in this case, the intermediate nodes now are by protocol effectively either break the edge themselves with this node, or if they don't do it, somebody else will break the edge with them, right? So the idea here is that if somebody in this network is not replying, right, that can be because of the node somewhere on the path is not replying. There is a edge broken. Now, edge breaking is not like that bad because it effectively means one connection is broken. There's a little bit of penalty from the
But here you're assuming like all the nodes on the path are following the protocol, but like it's possible, or like at least one node is following the protocol.
At least one node is following the protocol, yes.
But what if they all not following the protocol?
Yeah, so we'll get to that. We have the semi-magical solution for some of this. But yeah, at least one node is following the protocol. You effectively get a broken edge propagated back to Alice. And the idea that if Bob loses all the edges, that's effectively a slashable condition. Because that means that everybody who is communicating to it, it's not replying to them, right? So as more, obviously initially Bob has a lot of edges, and then Alice can continue, asking on different paths. And if Bob is really, adamant on not replying to Alice, it will end up effectively losing all the edges with all the related nodes, and in turn getting slashed, and effectively, in turn proving that it's not replying.
But you need to prove that it has lost all its edges.
Yeah. So the cool thing is we have a blockchain, and the blockchain, all of this doesn't work without some way to post all of this topography information somewhere, yes. Right? Because all of this right now is, if you don't have a blockchain, it's just a partially observed information for each node. Now, the cool thing is we do have a blockchain where all of these edges are actually recorded as payment channels. And so every time you open up a connection, you establish a payment channel on chain as well. And so you have a full topology recorded in a smart contract. And so now when, this condition happens, then the slashing happens on chain as well. And the Bob loses some on-chain stake that they have. So this is on one side, this itself is a networking stack, but on the other side, it does use blockchain as a, this global settlement layer, which is what blockchain is really good at. Now, the cool thing is then blockchain can use proof of response to effectively maintain its own networking connections, because now, again, if validators, for example, not replying to the data requests, they can get slashed not just for malicious block production, but now also for not being available for data requests, which is what data availability and all the other things are trying to ensure.
Is there a protocol on how much they should stake?
So that is, up to an application and kind of how it's used. I think For blockchain, the cool thing obviously is the validator is already staking, so we can reuse that.
Yes.
For things like up the stack, where obviously it's going to be some economic research that we'll need to do. Cool. So this is kind of, again, it's a new primitive, like on the on a kind of level of like proof of stake, enabling networking, incentivization, and verification. Do you want to talk a little bit more about blockchain parts?
Yeah, I mean, it has been talked about a lot, including in different whiteboard sessions. What should we talk about? I mean, obviously we can talk about the general stuff. So basically we have those blocks, and we have a shards, and each block contains chunks from different shards, and important thing is that there's only one chain, makes a lot of things simpler, and how the chunks gets verified. So since the release, Nightshade 2.0 release last year, is that now like on each block, so there's this like rotation of validators happening. So on each block for every shard, there's a random assignment of validator to shards. So they validate the state transition of that given shard in that block by verifying the state witness. So the witness basically is like a kind of a data that says the state, and then proof. So state is basically the state that you touch during the execution, and then proof is proof that the state is actually valid. It does belong to the state root. So today this is a Merkle proof. But the nice thing about it is that it doesn't have to be Merkle proof. Any proof that proves the state belongs to the state root would work. So for example, in the future, we can replace that with zero knowledge proof, and they'll be much smaller, and enable us to have better scalability. Okay, so I guess we can also talk about the runtime.
Well, I think the interesting thing that we haven't talked much in previous whiteboards is decoupling execution from consensus.
Yes. Okay, that is. Erase this.
So yeah, for context, Bowen introduced
I
that at
just
Redacted.
talk about it
Okay.
at the presentation today.
Okay.
But not in a lot of detail.
Yeah.
Because it's very complex. So it is kind of like something that's kind of already complex on its own. Like things like consensus, they're by nature complex. But when you like add sharding to it, it just become like complexity squared. So okay, so let's look at this. So today how it works is like, okay, you have block you produce, and like everyone go and process block, including like applying the chunks and whatever. And then they're basically like done here. Like here they're just like basically like they wait here. I mean, assuming let's say like a block is pretty empty, right? It takes like very little time to apply. They wait here until the next block is produced according to consensus, right? So what actually happens here is that the block producer is sending approvals to the next block producer approving this block, and then the guy, after receiving all the approvals, now he has all the approvals to produce the next block. But there's just this delay, right? So during this period of time, the node is basically doing nothing, kind of. Like, I mean, obviously there's network connection going on. It's like sending messages to different nodes, but it's not spending any of its CPU time actually doing the bulk of the work, which is like applying transaction and receipt, right? So if you think about what the blockchain is, it's just like this machine that continuously take like new transactions and apply them and get the new state. But here it's actually not doing that job. It just there's just this delay here that's idle. People have realized that this kind of sucks, meaning that we're not fully utilizing the power of every node. So instead, what we do is that we say, well, we want to better utilize this entire thing. So basically, it's split into consensus and execution. So in this new paradigm, we still produce blocks this way. It's just that the difference is here is that after a previous block is produced, you don't actually wait for the blocks to be applied and for the new state roots to be updated. You just like go immediately to the next block, trying to reach consensus on what the block is. So what that actually means is that it's basically like every chunk producer producing some chunk which package the transaction there, and they send to the block producer. They send the header to the block producer, and the block producer produce a block. And by doing this, it's basically just like a way to agree on what the transaction for like all of the shards are. It basically just like ordering and packaging transactions, and this just like goes on and on. And separately, there's like execution, which is like trying to catch up. So let's say we have let's say we get everything to work very well. You produce block every 200 milliseconds, so this chain would move forward. And then on execution, basically you're saying like you do the kind of what we do today, which is like you take a block, you look at the let's say each shard, look at the chunk, and then try to apply it. And at some point, this is configurable, but at some point you're done with applying some chunks. You can say, okay, I want to submit this state proposal. So on what basically this is like, this is roughly state root after block H. So basically this proposal says, here is a state root after applying this block, and it submits this proposal, and then it gathers this endorsement from the validators by doing the same status validation that we do. And then if it has enough endorsement, then it can be included in a block, which is part of the consensus chain. But there you're only validating that it has enough endorsement. So that's to certify the state root has been updated. So this way, the node is constantly doing work on like applying transaction and receipt and update the state, and you get better throughput this way. Another thing that is, I think, somewhat unique about this approach in the sharded setup is that generally with sharding, if you want to have low block time, it's somewhat incompatible with a lot of shards, because the more shards you have, the larger the variance will be between like receiving the chunks. So if you have that, if you have to wait for every block to be applied, then it's more likely for some chunks to be missed. But here, it kind of address that problem, because one, you don't actually need every single block to include a chunk from some shard, because it's kind of asynchronous between consensus and execution. But also that because you don't actually apply here, so it's much easier for like everyone to just like keep up with the pace and actually produce a chunk that contains the transaction. So it also nicely solves that problem.
The other interesting thing is, so right now in Near you have effectively a limit, like one transaction here can only execute for like 200 milliseconds. And that's partially because, I mean, even before we're reducing block time, like you need to give enough time to kind of between execution and starting to produce next block. And so here, if you decouple this, right, now it doesn't matter how long the transaction actually take. Like you can, you just order the bytes.
You can have longer running transactions just get updated later.
Yeah, and so things like Aurora, where sometimes like on EVM in Ethereum, transaction actually take can take 5 seconds to actually execute of real like crunch time, right? You can actually now apply this, and it can actually take whatever. On Near, it will probably take like 3 seconds, but yeah. So you can actually have like longer running transactions on top of already all the other stuff we have with a sync, right, where you can do other things. So it's really kind of improving fundamentally how like reducing latency, increasing bandwidth, and in turn also increasing what type of transactions you can do, which has already been like pretty powerful in Near.
So if I start a transaction, like you were just saying, that may take 2 seconds, and your block resolution time is faster than it took me to execute, and I was using data based on a block that is finalized at the start of the execution, is there a method of getting the delta state changes from the blocks that may resolve in between the start and the end of the execution? Did that make sense?
So the idea here is like the transactions are queuing up, right? So you can think of this like the consensus part is just feeding the queue of transactions. So like every time the block is produced, it just puts things into a queue, and then this execution just takes it a queue. So if there's other transactions touching the same state, the same contracts, they'll just go into a queue and they'll start executing after. So to give you an example, like let's say there's like Aurora transaction 1, and then it will like start executing Aurora transaction 2. Now, because near is parallel, you can have like ref executing here.
Yep.
You can have some NFT minted in parallel as well. But on the same contract level, which is kind of our level of parallelization right now, you will have them sequenced. And so they'll just go into queue and wait.
Yeah.
Yeah, so indeed really cool. I mean,
Yeah, it's really nice.
solves a lot of interesting things for near, but also kind of pretty innovative across the ecosystem. So let's go to chain signatures.
Yep. So this is, I guess, also connect with TE. So basically, so what this thing is that let's say you have an account, or let's just say smart contract. So it can be a regular account as well, right? So this is a smart contract on near. So today, just like regular smart contract, and just the thing you can do is within the near ecosystem, right? But what this chain signature allows you to do is that now it suddenly have addresses on, let's say, Bitcoin, on Ethereum, on Solana, and let's say Base. So this smart contract itself has a count that it controls on all of those chains. It's a very interesting paradigm because now what it can do is literally you can have some logic that allows it to sign transactions for each of those chains. And then some relayer can go and take the transaction and go and execute on those chains. So it enables a lot of interesting use cases, especially in like cross-chain DeFi. Like for example, if you want to like bridge like some token from like one chain to another chain, historically the way you do it is like you prove that something happened on one chain, and then you go and send the proof on the other chain. The other chain verify, okay, there's a proof, and then it like does token minting or like unlocking. But here, like what it can do is literally like it can just like release. Let's say it has this address on Bitcoin and it holds on Bitcoin. It can sign this transaction and release Bitcoin or like send Bitcoin from that address to some other address directly. And this is both easier to maintain because you don't need to worry about this complex logic of verifying between chains. But also it's actually faster because like a native transaction is sent. The latency is basically the latency of that chain, of the destination chain. So this is more like from kind of the use case perspective, and near intents, for example, is a big use case of chain signatures. And in general, like there are people building multi-chain lending, borrowing, multi-chain asset management. You can have like one contract that implements some like DeFi strategy that manages accounts on all sorts of different chains and does like rebalancing. That can even be controlled by like AI agents. We can talk about that. So a lot of cool stuff can be done from this primitive. Should I talk about how it works?
Maybe briefly, yeah.
Yeah.
Like the final state or current final state.
Yeah. So like roughly there's some set of nodes. So it's like MPC nodes. So each of those nodes roughly they hold a key share. And and the key share doesn't, so you need a threshold, there's a threshold, you need a threshold number of them to participate in a signing request in order to generate a signature. And the signing request it happens on near, so there's like a near, it actually runs a near node that indexes the chain, and when a signing request is triggered, it verifies that it's actually a correct signature request by, that's just smart contract logic, but here it's just to verify the state transition is correct, so no one is trying to maliciously attack by generating a bogus request. And then after it got the request, it started the threshold signing process, which is the threshold cryptography that I won't get into, but then in the end, the signature is produced and then submit back into the blockchain. And the interesting thing here is that we want this MPC node to also run inside TEE to make sure that the key share can never leak. So generally the problem with MPC is that it doesn't have a good defense against the long-range attack, meaning that if some old set of participants collude, they can still recover the root key, and then everything is screwed. So inside TEE, like you have basically you only allow the key share to be held in unencrypted form inside the TEE, and when it needs to be persisted, encrypted by the TEE's encryption key, so that even if the node operator is malicious, there's no way they can get it out. So it makes it much more secure.
Yeah, so maybe that's a good transition to TEs,
Yep.
right? So I kind of mentioned this in my talk as well, but just like on a high level, we have the hardware, like for example, CPU, and so there is a specific way where you can actually run a full operating system image inside this secure enclave in such a way that kind of processes outside, so this is secure enclave, trusted execution environment, processes outside are not able to access it, right? So traditionally, TEs have been kind of considered A, very hard to use, and B, very insecure because of two reasons. One was that the way to run software inside them required to actually write in a special way using very specific APIs. So previously it was Intel SGX. It effectively required to rewrite everything in C. It had very low level APIs. It didn't have, for example, parallel instructions like SSE. And so it was very limiting what you can do with it. Plus, there was a lot of known side channel attacks on how to actually extract information from it. Now, since about like March or April last year, there's a new kind of generation of trusted execution environments. With Intel, it's called TDX, Trusted Domain Execution. There's a version for ARM. There's a version for AMD. And so those allow to actually run a full operating system image inside this environment. And so you can literally prepare, think of it as Docker. You can spin it up there. And now what you can get, which is really interesting, is that when some computation is done, you get effectively a certificate that this computation was done on this data. And importantly, only this computation was done. There was no other computation done on this data, which is really important for a lot of the use cases we just talked about, right? Because if you think of the MPC that Bowen described, well, you want to know that only the calculations that you asked MPC to do was done, and nothing else, right? It didn't try to extract the key,
Yep.
didn't do anything with it, and actually maybe even deleted it so that this shard is not even valid anymore going forward because it doesn't exist. Similar with proof of response, right? This ensures that nodes actually following the protocol in the whole network of the nodes that following the TE. So there's a kind of this concept of quote which TE can return, and so on top of this primitive, right? There there's a few different bits and pieces that are being built to enable this. So first of all, there's kind of reproducible Docker builds. That especially File Network been pioneering on how to make it really easy to distribute software in verifiable way. So you actually get effectively you can upload a specific Docker container, which the hash of which is known and it's consistent, and so you can actually look at source code, verify that the source code is not doing anything malicious, reproduce the Docker, compute the hash, and when you do some computation, it actually proves to you that this hash of a Docker is running inside TE. Right, so that's kind of basic primitive. You get this Docker container was run inside TE on this execution, and only this thing was done. Now, kind of what this allows to do, Kendall was talking about, is the concept of shade agents, right? Where now you can actually call, for example, some execution, and then go back to the blockchain, right, and post that, hey, these calculations were done on this data, and this is the outcome, right? And so your smart contract can effectively receive outcome, verify on-chain that this, quote is correct, that you actually have indeed used this, done this execution inside TE on this data, only this thing was done, and this is the outcome. And now this outcome can be used somewhere in smart contract. To give you an example, you want to build this rebalancing portfolio. You have the chain signatures to hold assets on all chains, but who does rebalancing, right? Like, what is the logic of rebalancing? Well, you can actually run arbitrary computation. For example, go read Twitter, fetch data from Kaido, decide on a new allocation in the index, and then return back this new allocation, right? And then, maybe it does like some cross checks on a smart contract level, and then verifies that indeed, let's execute that rebalance.
Yeah, I think an important thing here is to know is that there is a way to verify this attestation without going to Intel server. Basically, there's a database that they publish that can be put on chain, the database of certificate that can be put on chain, and then that can be used to verify the attestation, which is what shade agents do.
Yeah. And similarly, like if you are our proverbial Alice who wants to do some computation off-chain, right? She can connect to this node through TLS, so through encrypted connection. So this node exposes effectively, it's a certificate proving that it runs in the same Docker. And so then you can, encrypting with a certificate, communicate some private data that, again, this node, let's say this is our semi-malicious Bob, cannot see whatever the data coming in, what happens inside. So some computation is done, and then the response comes back, again, with this quote, right? So now you have a full end-to-end confidential, effectively, computation done on remote server, and you know that only this computation was done. For example, it removed all the data afterwards. It didn't save it. You know that it ran exactly as this AI model or this AI agent, and you get back kind of certificate that the answer is this. Right. So this enables effectively both on-chain and off-chain actors kind of communicating with this TE node to really do confidential computation in off-chain case or verifiable in the on-chain case. So kind of, but this is like a single node, right? So okay, what happens when there's like lots of these nodes? How do you actually manage this? Well, this is where proof of response comes in, right? Because the reality is like there might be some node, and when I say like this is any arbitrary Docker, I mean it. Meaning we've, for example, spun up our like Postgres-like database running inside TE, right? So you can actually literally have a private state for your shade agents, on-chain agent, have private state running inside TE that you trigger, do some calculation, and the output becomes public on-chain or private off-chain, right? So like it's an arbitrary, like complex software that runs there. And so now you can have lots of these TE nodes that join the network. They will need to stake something to participate in proof of response. And so now you can actually have an ability when you send a request to prove that one of them is offline or not, right? So this gives you kind of this liveness guarantees from a network of verifiable nodes. And so you actually have a fully verifiable live cloud. Obviously, like if the node is offline, you need to effectively reroute to another node. So there needs to be a like additional protocol like for kind of load balancing the work, etc. But overall, this gives you kind of a verifiable cloud, something that if you've been in crypto in 2018, everybody was promising you. This is actually it. Offers effectively a system to achieve that by combining proof of response, TE cloud, using blockchain, and then obviously leveraging chain signatures to go multi-chain.
Yep.
Okay. So if you're not bored yet, we have more stuff. So all of this is cool. The next level of this is the idea of intents. So intents is really more from a kind of user perspective and kind of higher level developer perspective. If I have some requests, right, and I actually don't want to figure out how it should be done, right? So this is like, hey, I want to rebalance this portfolio. I don't want to actually figure out exact, swaps that needs to happen. I want somebody else to do that, right? So you can communicate this request. So here you have some way of communicating. So for example, this can be centralized, running inside TE with verifiability. This can be our decentralized TE cloud, where this propagates. And so you have other parties, which can be either verifiable or not. So this can be some, like friendly face, and this can be some things that's running inside TE that can respond to this saying like, hey, oh, you want to execute this complex procedure, I will do it for you, and this will cost you this much, and I'll do it in this long, right? So the simplest example of this obviously is swap one Bitcoin for whatever 100K USDC. Somebody's like, cool, I'll do it maybe 99,500. Somebody's like, no, I'll do it for 100K. And the cool thing compared to usual blockchain, where you would submit this request on chain, and then effectively now everybody can observe it, and you have minor extracted value. Where people try to front run it. Here, because it's a private request, and you're actually getting the quotes, you're getting the kind of, hey, how much you would do it. So it's an interactive protocol. You choosing the best option, right? So there is no way to front run you because you choosing what's the best option going to be, and then you already submitting effectively two signatures, your signature and the solver signature on chain, to actually set to commit to this outcome, right? Now this protocol can be a bit more complex. There can be like some escrow time where there may be dispute because, for example, you said build me a building with 5 floors. It said like, okay, cool, it's going to take a year, and I'm going to do it for whatever $5 million. And so this $5 million are actually going into escrow, and then if the building is not built, there's a way to resolve that and get the money back, right? So simplifying, but that's kind of allows you to have this complex off-chain negotiation protocol, figure out what you want to do, submit this, start executing and disputing. TE offers you like additional benefits because now, for example, who doesn't like launching new tokens? Well, you can actually launch new tokens inside TE itself. So you have new token on-chain, so XYZ token. And so all of the XYZ token is owned by the account inside this TE. And so when people want to buy it, the TE is actually market maker, right? So you have a fully like confidential and also verifiable, you know exactly how it works market maker, right? So this can be as simple as your Uniswap formula, or this can be as arbitrary as have you tweeted today about this token, then you're allowed to buy, right? It can be arbitrary logic that actually runs here as a market making logic that actually responds to requests from users. So this actually solves one of the fundamental problems with blockchains where however you parallelize it, if people are trying, like if 10 million users are trying to target the same piece of state because everybody wants to trade Trump, it doesn't matter how you parallelize it, that piece of data is congested. And so this actually allows to have, you can arbitrarily scale this number of TEs that can respond to this request that control the supply, and so they can all effectively reply to different users. So you can actually have a scalable, market making, fully verifiable through the TE, and replying through intents.
Yeah, I think the interesting thing here is it's not limited to trading tokens or swaps. It's more general, and it can be extended to things like commerce and just buying a laptop or whatever you want to do.
Yeah, so the example we showed, this is more going into AITP already, but yeah, you can say, hey, I want to buy headphones. Somebody's like, well, here's some options for you, right? An agent replied. You're like, cool, I'll select this option. Let's go to the process. We escrow the money, and then when the product arrives, right, we resolve it or dispute it if it didn't arrive, right? So this actually allows to do like more traditional commerce in this way, and like general payments infrastructure. Think of credit card payments, but now done through these flows. And again, because you have guarantees, you can have guarantees on some of this other side as well. You can actually do a lot of new things in this way.
Yeah, it's also very flexible. You can do like OTC and stuff like this. Still use the same framework to settle. And it's not like just like X times Y equals K. It's very flexible.
This can literally have like a Twitter whitelist. It can have like an arbitrary formula of market making, etc. So, but it also can be like any arbitrary AI code that runs whatever, right? So that's kind of the idea. Is like we're effectively moving from trying to fit everything into blockchain to effectively have like an EC2 level verifiable compute that you can then interleave with effectively like arbitrary requests and responses through this network. So on top of that, we build effectively the agent stuff where these agents are now communicating with each other. And so AITP is really just conglomeration of all these products, right? Where it allows effectively one party to initiate some communication, and then parties to exchange, structured data. Like, okay, I want, request some data from you. I want to request signature. So let's say this is agent B. This is agent A, and you have maybe like user. And so, kind of the idea of AITP, you can have like multiple of these parties in the same conversation, and some of this gets replied directly by agent A, some gets propagated to the user. So you have like a full flexibility of effectively decomposing intents into like any number of participants and kind of exchanging all this in one communication. But the cool thing is because it's kind of maintained, think of it as a thread or as an email thread, you can then, if something, like if you have a dispute, right, let's say product didn't arrive, agent didn't do the good job, you can effectively add like another dispute agent, for example, who joins the thread and like, okay, what happened here? Like, what did you promise? What's the process, etc. And this itself, can escalate to like court, because this has like a full like conversations logged as well that is only shared between these parties until new parties are joined. So kind of AITP effectively creates like this overlay over all of this to kind of on the like agentic level to kind of join all of these pieces together and enable them to trade, converse, and interact, as well as do business, do kind of transactions, exchange private data, UIs, and other parts. So, point is, all these pieces effectively working together. They all build on top of each other, and we're effectively enabling this vision. We talk about like how AI is actually gonna be your interface through the through Web3 and Web2, and all of these pieces are really kind of powering that future.
Yeah, it's very exciting. And,
yes. So still a bunch to build, but we already see. I mean, you saw the demos. I think we have more demos actually. I want to show more demos, but
yeah.